the last topic in our applications unit is on optimization problems. And this is something that mathematics is very interested in. You started in grade 11 when you had a vertex and you tried to find that vertex as a max-min problem. Do you remember those questions where one of them was you're building a fence on 3 sides and you want to have the maximum area? Or there was questions where if you plant more trees, you have less apples per tree. How many trees should you plant to get the most apples possible? So the thing about maximum and minimum problems, now that we have calculus, we know whenever we have a maximum or minimum on a graph, the tangent line will be flat and it'll be equal 0. So we're going to actually be able to solve some of the questions we solved in grade 11 much, much faster than the way that we did it in grade 11. So how do we solve optimization problems? We create an equation, we assign variables, we take that equation and find the derivative. Set it equal to 0, because if the tangent is 0, that's when you're going to have a maximum or a minimum. So here's an example. A ball is thrown upwards at a time t seconds. Its height meters above the point of projection is given by this formula. Calculate at which time the ball is at maximum height. So starting off in grade 11 with this parabola, you would have had to complete the square to find the vertex. Now that we have calculus, we can just find the derivative, set that derivative equal to 0, and we can find out that at 7.5 seconds, it will be at its maximum height. The actual point will be 7.5 comma, and we would have to factor this or plug 7.5 into the original equation, which happens to be, I'm doing a random guess there. Well, not too random. Did a little bit of math on that. Someone could plug that in. I don't really trust my 7.5 times table that much. A couple of other things I noticed about this question. Remember yesterday when we did kinematics that if this was a real life question, the value in front of t squared should be negative 4.9, and the value in front of t squared here is negative 1. So in other words, this object has been thrown up in the air on some different planet that has a different gravitational pull than Earth. So here's an example of a question that isn't actually written well. I probably wrote it. Maybe it's written well, so we discussed this. Was this right? 56.25? Someone check it? Oh, we'll just assume it's right. Oh. Here's another one from grade 11. Fred wants to enclose a rectangular parking lot with 60 meters of fence. Someone should tell Fred that if he encloses it, nobody will be able to park in there. But we will not worry about that either. Okay? There's a building on one side, so this is a top view. Here's the building. And parking lot is going to get enclosed with fence, so whichever cars are in there during the day, Fred is hoping to keep them. That is his plan. And he wants to steal as many cars as possible, so we want to find the maximum area that Fred can enclose. So we have some options. It could be like 10, 10, and 40, 20, 20, and 20. we have different options. Now, what we do is we choose a variable. I would choose this side to be x because that makes this side also x. And if you've used up that amount, whatever will be here would be 60 minus 2x. So our goal is to choose one variable, write all of our information within that variable, and now we can write out a formula that our area is length times width. And if I distribute, I get 60x minus 2x squared. A couple of things that are sometimes hints in these questions. If you want to find a maximum area, that means your equation should be area equals. If you wanted to find a maximum profit, then you need to make an equation profit equals. Once we've got our area formula, if we find our derivative, set it equal to 0, and solve. We get x is equal to 15. Reread the question. What are they asking for? They're asking for the maximum area. Well, that's 15. This side will be 30. 15 times 30. Meters. I don't know how big of a parking lot that is. How many cars did Fred steal during this time? And I don't know if he's making a chain link fence, then the owners would come back and be like, wait a minute. But again, another good example of a fairly good word problem to work on that has little glitches. Oh, but you know what's really cool? Sorry. What's really cool about a question like this is we can now with calculus, maybe you noticed this pattern back in grade 11, maybe you didn't. But if I do this question again, but I just say instead of starting with 60, I'm going to use a big T for the total, right? Because we could have started with 80. We could have started with 100. We could start with any total amount of fencing. So I'm going to use a big T there. I don't know what that number is, but no matter where I use that, this 60 all the way through, and what that means is that to find the maximum area in this situation, whatever your total is, this side will always be 1/4. So if you started with 100, it'll be 25, 25, and 50. If you started with 200, it would be 50, 50, and 100 will give you the maximum area. And so what calculus can sometimes let you do is start off with just, something random, and now you've solved them all. And I try to never tell grade 11s that pattern, because then they stop doing completing the square completely, and they're just like, oh, I'll just memorize that it's always that shortcut to figure it out. Here's one from grade 12. A rectangular sheet of cardboard measures 10 centimeters by 7 centimeters. I'm going to draw a picture of that. This is 10 centimeters, this is 7 centimeters. And we're going to cut out little squares out of the corners. And we don't know how big those squares are. So we'll call the side length of them x. We then would fold along these two blue lines and these two green lines. After that's cut out, if we fold along those lines, we would make an open-ended box. Can you see that the length of my blue line started with 10, but I subtracted x on both sides? And can you see that the length of my green line started with 7, but I subtracted x on both sides? If I draw what I have as a three-dimensional shape, so that balancing act, switching colors. Oh, I was doing good. Until this line looks a little bent to me. Can you see if you fold the green ones up, fold the blue ones up? This is the shape that you would get, and it has a volume, length times width times height. The volume of this would be the length, 7 minus 2x, the width, 10 minus 2x, and the height, which is x. In grade 12 pre-calculus, you graph this, and then you used a graphing calculator or Desmos to find the maximum. Now that we have calculus, well, I could find the derivative, but it's a big product right now. You could do a not very nice product rule of this. However, it probably makes the most sense to multiply it out. I'll multiply these two first, so I would get 70 minus 34x plus 4x squared. And then multiply that through the x, 70x minus 34x squared plus 4x cubed. That's the equation when it's multiplied all the way up. So in grade 12, the best we could do for a maximum would be to use some sort of graphing technology. Now with calculus, we can find the derivative, 70 minus 68x plus 12x squared. Set this equal to 0. Notice you can factor out a common factor of 2, 6x squared minus 34x. Plus 35. And unfortunately, I don't think this one factors very nicely. But if it was a university class and you weren't allowed a graphing calculator, you could still solve this with the quadratic formula. However, if you were on an IB exam, and you were allowed your calculator anyways, then I would recommend taking the original equation, graphing it, and just finding the maximum. So what would that look like? Well, if I took out my calculator, went to y equals, I typed it in exactly as I see it, 7 minus 2x, 10 minus 2x, and x. And I hit graph. It makes an x cubed graph. Right now, the maximum is not showing. I do see a minimum here. So I can go to my window and maybe I want to see some more my y max to 50, maybe that's enough for me. Oh, worked out pretty nice. To see the maximum, okay? Something else within this question that sometimes comes up on an IB exam is you have to think about how much of this graph actually makes sense. So for example, I've got an x cubed graph. Its domain is everything. But I hope you understand that these negative values of x make no sense in this question. You can't cut negative squares out of your corner. When looking at this graph for volume, some other things. Oh, here's a section of the graph where the volume is negative. That makes no sense. You can't have a negative volume. What's happening here? This seems to go between 3.5 and 5. But what happens once I start cutting out squares that are more than 3.5? Notice there was one side that started at 7. If I cut more than 3.5, that side is gone. There's no square left. So really, the only part of this graph that makes sense is the domain where x, well, not even equal, we have to cut out something bigger than 0, because if you don't cut out anything, you have no volume because it's still a flat piece of cardboard. And we can't cut out 3.5 because then the other side is completely gone. So our domain that makes sense is only looking between 0 and 3.5. On our graph, that's only this section here. So if I had a graphing calculator, I could graph this. I can calculate the maximum, number 4. It asks for a left bound. I push enter at 0. I'm going to put 3.5 for my right bound. And it finds it there for me when x is 1.35. And at x equals 1.35, my graphing calculator also tells me the maximum value at 42.4. I should include my units. So the question started off with centimeters. Okay, find the maximum volume of the back box. And again, based on the values that are given in this question, you would have a calculator. So even though it's an optimization question and you could use derivatives to find it, if you have your calculator and you're able to graph it and get a maximum early, the IB loves it if you can find those ways. It's like, it's not cheating if you've got a shortcut way to get the answer right away. They're actually wanting you to think that way and find the answers that way. AB and BC vary such that their sum is always 6. So getting good at labeling things in here, I mean, this question is leading you. It says, if the length of AB is x, write down the length of BC. Well, if these two always have to add up to 6, BC would have to be 6 minus x. And now we can write an area formula. Area of a triangle is base times height divided by 2. So what I'm doing right now is I'm taking base times height divided by 2. I'm using my algebra skills to get it into a form that I feel would be easy to take the derivative of. So I had 6x minus x squared over 2. I divided both of them by 2 to get 3x minus 1/2 x squared. Now my derivative just becomes 3 minus x. Set the derivative equal to 0. And we get x equals 3. So what's the maximum area? Well, so base, the height would also be 3. Was there units in this one? Centimeters? The max area is now 4.5 centimeters squared. So our job is to see if we can write the equation based on the information given. And you did these equations back in grade 11, so that part of it is a review. Product of two positive numbers is 48. Find the two numbers so that the sum of the first number plus 3 times the second number is a minimum. Okay? So we need to decide what our first number and our second number are. We choose one of them to be x. And now we have to figure out what the other one is in terms of x. If their product is 48, then the second number is going to have to be 48 divided by the first number. And now we've written both numbers in terms of x. Now we want to find a minimum sum. So I'm going to write the variable s for that minimum sum. Well, I'm going to write s for the sum, and then once we find the derivative, that will let us find the minimum. What are we doing? The sum of the first number, which is x, plus 3 times the second number. This is what we want to find the minimum of. As far as writing this and simplifying it, 3 times 148. And I'll change the dividing by x to an x to the minus 1, so I can use easy derivative rules. My derivative then would be 1 minus 144 x to the negative 2. I can set that equal to 0. And this is what I have to solve. Algebraically, I might move the negative 144 over x squared to the left side, multiply both sides by x squared. And when I square root it, I get that x is equal to plus or minus 12. Two numbers are, two numbers, we need a minimum. So we haven't Here's an interesting thing here, right? When we find our critical points, in the previous question, we only got one answer. And if you only get one answer, and it's asking for a maximum, or it's asking for a minimum, that has to be the one, right? There's never going to be a trick question where they say, find the maximum, and then they're like giggling in the background. You don't hear this on the IB exam, but they're giggling on the background. There's no maximum. I wonder if they'll find out. If they say find the maximum, there will be a maximum. If they say find the minimum, there will be a minimum. But in this case, we have two possibilities. Does this mean that they're both minimums? No. One could be the minimum, and one could be the maximum. Or maybe they are both minimums. That's what we have to find out. So when you find your derivative, we need to find out if it's a maximum or a minimum. So we need to either use the first derivative test or the second derivative test. Knowing you guys, you probably like the first derivative test better. If I plug in negative 12 and 12, and I go to my first derivative, and I check if I plug in values within here. Oh, we also have to add 0 to our number line, because 0 is a non-permissible value in our derivative. So we have to check these places. Where is our graph increasing? Where is it decreasing? If you plug in something larger than negative 12, like negative 20, negative 20 squared would be 400. 144 over 400 is a fraction less than 1. So if I did 1 minus that, this would be positive. This part of our graph would have been increased. Then, if you plug in something between 0 and negative 12, like negative 1, this is going to be 1 on the bottom. You're going to subtract and get a negative number. And so negative 12 is actually a maximum. If I plug in something between 0 and 12, that's negative again. And something bigger than 12, that will tell us that only the value of 12 is our minimum. Two numbers that give minimum are 12 and 4. I find the second one by going to my second number. 48 divided by 12 would have to be 4. So we have an open box, square base, total surface area of 192 centimeters squared, if its volume is a maximum. Okay? So, draw a picture. We've got a height. I'm going to label things this way. It's a square base, so the bottoms are x's. I would argue that if this was an exam question, it's open to some confusion, okay? Because I've seen this question interpreted two ways. If you have an open box and you're asking for surface area, you would have like the bottom inside the box and the bottom on the bottom and four sides on the outside of the box and four sides on the inside of the box. Is that the surface area? And then I've also seen other places think, oh, we just want the outer surface area. Just the bottom and the four sides, but not the inside. And so it's unclear a little bit, because depending on which person is writing this, you get different perspectives. So we can solve it either way. We can solve it, do you want to do it simpler, where you're just doing the outer surface area? Okay, we'll do it simpler, we're just doing the outer surface area. Can you see that the outer surface area would be the bottom, which is an x squared, and then you would have four rectangles that are all x times h. And what do we know about our surface area? We know that our surface area is 192, so that gives us this equation. Right now, we have two variables. The volume of this box is length times width times height is x squared times h. And currently, we have two variables there as well. When you have two variables, we can't take the derivative of it yet. At least we don't know how to in this calculus course. Okay? But if we could rewrite the volume with only one variable, then our life would be easy. And since we have two equations with two unknowns, I could take this surface area formula, I could subtract the x squared on both sides, then divide both sides by 4x, and I would get the height by itself. This would allow me to substitute in that for the height. Not a nice equation, but something we can simplify, right? The x squared and the x on the bottom could cancel out. If I cancel out one of these x's with this x and distribute the other one, I'm going to get 192x divided by 4 minus x cubed divided by 4. Which simplifies even further to 48x. So the volume has to be a maximum, was part of this question. So if its volume is a maximum, we find our derivative, 48 minus 3x squared divided by 4. Set it equal to 0. And solve. Oops. Oh. This is so nice. We got two answers here. Do we need to do the number line in this case? No. Because one of the answers doesn't make logical sense. You can't have the square base being -8 centimeters. So the only answer that makes sense is 8. And if the only answer that makes sense is 8, then the base has to be 8. We can go, the dimensions are 8, do my units here, centimeters, 8 centimeters by 8 centimeters by, and to calculate my height, well, I created a formula that said the height was equal to 192 minus x squared so I plug it into that height formula. And I get the dimensions. Everybody good? Okay, 2 questions to go. So this is where businesses start to look at these problems and use calculus to make as much money as possible, okay? The cost of ordering and storing X units of a product, they've got an equation that they've developed for this, right? It costs you less money if someone brings them all at once, but when they bring them all at once, now you have no room to store them, so then you might have to store them somewhere else, which costs more money, so then it's like, okay, that's not necessarily good to do either. So here we have an equation, and we want to find out how much we should order to minimize the cost. So we've got our cost equation. It's really nice that it's already there. We can, in fact, I'm going to take a moment before I find the derivative. And just change it to a nice form, so that when I find my derivative, it's easy. So I set my derivative to 0. I'm going to move that x squared to the bottom. Again, only the positive one makes sense. And I saved my favorite question for the end. And I'll tell you why this is my favorite question. This, in my opinion, is, well, the numbers in this question were designed so they work out nicely and make everybody happy. But in real life, I would say what this is really looking at is a closed right circular cylinder You see those all the time. In food products or drink products, we call those cans. In math problems, we call them right circular cylinders. But that's just a can, okay? And this is very important. Most of our cans, like if you buy a can of Coke, it has 355 mils in there. Coca-Cola is making all of their drinks that size. In fact, all cans of pop drinks are that size, 355 mils. Why did they make them in the shape that they make them? Why did they choose a can? That's a cylinder, okay? And if they choose a cylinder, why aren't they longer and narrower or shorter and fatter? Well, what we're going to find out in this question is if you get a certain volume, there is a certain relationship between the radius and the height that can minimize the surface area. And if you're minimizing the surface area, you get the same amount of drink into that can by using the least amount of aluminum. That's important for Coca-Cola. Because if you could figure out a way that Coca-Cola could save 1 cent per can of Coke, you'd be a millionaire. You'd be like, here's my proposal. I'm going to save you 1 cent per can from every Coke can that you produce from now on. They're like, can we see the proposal? Only for $1 million. For sure they would pay that. Because they would make that money back so quickly, right? And you'd be a millionaire. So this question is basically getting to that. How do we figure out what size we should make to minimize the surface area if we have a certain volume that we want? Now, in this question, it's not 355 centimeters cubed. It's 54 pi, which is probably not, I would love that. Can you imagine how much is in this can of Coke in there, right? 54 pi. Coke for math nerds. And the units are all funny. No. But the nice thing about this question, by using a not nice number like this, we're going to get nice answers in the end. If we use 355 centimeters cubed, and everybody knows that 1 centimeter cubed is 1 milliliter. You heard that before? For like volume to milliliter conversion. Technically, it's only for water, but most drinks are close enough to water that would work. Now, we need to start off by showing that the total surface area of the cylinder, so we need to draw out our cylinder. We need to figure out our surface area formulas and our volume formulas for a cylinder. Volume of a cylinder formula is the area of the base times the height. And the surface area formula for a cylinder is 2 circles, one at the top and one at the bottom. And then, this is like one of my favorite formulas too. The cylinder formula. Have you ever taken a can of soup at home and taken off the label to see the shape of the label? Right? If you peel off the label and open it up, you get a perfect rectangle. Right? If you're curious if that happens all the time, take all the cans that your mom or dad has in their pantry, take off all the labels. And say, oh, another rectangle. I wonder if the next one's going to be a rectangle. They'll be very happy when they go in there later and there's no labels left on any of the cans, so that you get surprise suppers for the rest of the week. We were going to have soup, but tonight we're having pineapple. What happens then is that rectangle that you peel off, right? If you cut it, right, oh, let's do it in blue. If you cut it right here and peel it off, the length of that rectangle right here is this length right there, which is the circumference of a circle, multiplied by the height of your cylinder. So your circumference formula and your height make that rectangle, and that's where your surface area of your cylinder comes from. This is a formula that I don't have memorized. I just redraw it every single time. I think about the circle on the top and the bottom, and I think about the rectangle, and there we have our surface area formula. Now, we want to show that the surface area formula in our case is equal to this equation. Notice that there's no h in the equation. We have, just analyzing a little bit, we have this part so far, but we need this part to look like this, and there needs to be no h in there. So what I need to do is I need to use the volume to get h by itself, and then I could plug that into the other equation. How can I use the volume to get h by itself? Well, I know that the volume is 54 pi, and that the volume is pi r squared times h. So I can rearrange my volume formula even those pi's will simplify nicely, so that h is equal to 54 over r squared. And I can now take my surface area formula, 2 pi r squared plus 2 pi r, and instead of h, I can substitute in 54 over r squared. One of the r's on the bottom is going to cancel out with that r. Times 2, there's our 108 pi, and we're left with an r on the bottom. Is that what we wanted to show? Yes. But and now we can actually solve that Coke problem. What should the radius and the height be to make this a minimum? The surface area minimum. That will help you solve what should the radius and the height of that can be for Coca-Cola to use the least amount of aluminum possible. So when we get to part B, we now want to, I'm going to rewrite that r to the minus 1. I'm going to find my derivative. Set my derivative equal to 0. Now you have the r squared on the bottom of your fraction. You could get rid of that. Well, what we did in the other ones is we brought the thing over to the other side, but we have r in more than one place here. But if you would multiply everything right now by r squared, you would get rid of your fraction. But that would give you an r cubed here. And our numbers haven't been nice, but don't worry. There's a reason we started off with not very nice numbers. So according to this, we can move the 108 pi to the other side. Divide both sides by 4 pi. Pi is nicely simplified. Oh, and you get 27 equals r cubed. Cube root both sides. Are we dealing with centimeters here? Yes, we are. So r would be 3 centimeters. And h, find the radius and the height. So now we had an equation where h was by itself. Oops. H is 54 over r squared. And since r squared is 3, r is 3, 3 squared would be 9, 54 divided by 9 would tell us so according to this, the height should be double the radius. I think about a height of a can, I almost think that the height is double the diameter when they figure out the actual height. But problem with a can is they bend it a little bit, they have to put a seal on it, so there's logistic problems. You can't just make a perfect cylinder and make a can, because then production might be more expensive. So all of these variables come into play. I can guarantee you right now, the shape of the can that's being used is strategic to save all sorts of things. Okay? Cans fit nicely into a box. Okay? They're cheaper to make than cubes. Cubes are a little bit awkward to make, so that's why they go with a can. The best shape for minimizing surface area but maximizing volumes is actually a sphere. But the problem with spheres is people buy drinks in spheres and they put them down, they roll, and they spill all over the place. So there's probably reasons we don't get cans in the shape of a sphere. But this is the fascinating thing, that mathematics and businesses all intertwine. And so they're trying to save money in all of these areas. And if they can do that, that means they can make more money in the end.